Hello everyone, can you hear me?
Yes, sir.
Okay. So today we'll be going through the week 2 of this course. So we'll be going through linear regression and decision trees in detail today. So we'll do problems on these two topics that have been covered in this week, and we'll also do some programming. So I hope that you all have gone through the videos of this week, uh, because that's the topics we'll be covering now. Okay. So let us start with, so people are still joining. Okay. uh, there is a box, so we'll start off with what is entropy. So before we come to this, hello. Okay, so let's start off. So entropy of a distribution S is given by this is for a continuous system. So this is entropy for a continuous system over the entire probability space. So we'll not be dealing with these sort of random variables here, because we all know that in machine learning we all deal with discrete variables. So what happens is, I'll give you the intuition of entropy now, and then we'll go to the problem. So this will be discretized to, so there is no I here, so since P is a distribution, so this will be this is discretized. So Pi is the probability of each event. So how can we understand? So say, think of, so x is a random variable that takes values small x1, x2, dot 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 xn. So what we do is, and I define Pi as the probability of the random variable x taking value xi. So in that case, the entropy of this is given by this function. So what does this signify? So for all the possible values that the random variable can take, we have a sum of the log of the probability multiplied by the probability. Why does this work? What does entropy generally mean? So in thermodynamics and information theory, entropy means the order of it measures the degree of randomness. So it's very clear that whenever we have to generate a function in information theory such that whenever the more the entropy, the more the randomness. So we can clearly see that, I'll give you an example here. So if one of the Pi is equal to 1, then the rest of the Pi's will be 0. So if you don't understand, you can always ask me in the chat, or you can stop, you can introduce yourself and ask by unmuting yourself. So all the pj's will be 0. Then you can clearly see for this distribution, say this is h, entropy, say d of d will be 1 into log of 1, and these are all natural, these are all log base 2 here, because this deals with coding and all, so we just consider that it's log base 2. You can take any log, it doesn't matter to be exact, but still let's take log base 2 here. So here, hello,
Mainan sir,
yeah,
could you please explain that what is the entropy in layman term? Then we will understand. We will try
yeah,
to
that's what I'm trying
understand.
to do. I'll just tell you.
It's just a mathematical means we are not able to understand what is entropy.
So I'll tell you the layman term as well. So there's no, I'll just show you this, then I'll come back to that. I explained that just now. I think you missed it. Anyways, so you get 0 for all the rest. So log 0, you take some epsilon tends to 0. So this is also 0, and this is also 0. So this is why I try to motivate using this example. So you can clearly see for the ith element, the probability of that occurring is 1. Means it always occurs, or it almost surely occurs. So we know we don't have any randomness in this distribution. So here there is no randomness. So we see that the entropy is 0, because there is none of this. We don't get any more. Whenever we sample something, we sort of don't get any more extra information from the distribution. So this is, I'll come to what exactly does this mean now. So more the randomness, so the probability of each being equal to some being close to each other, so total, that is total randomness. In that case, the entropy should be maximum. So entropy means how is the disorder in the system. So that's, we clearly know that in entropy in physics means we are seeing how the molecules or the particles are moving away from one another, or the degree of randomness. In information theory, it deals with the probability distribution. How are each of the realizations of the random variable probable, equiprobable, or similar to each other. So each realization, say a discrete random variable takes xi, so in that case the more this the more each of the probabilities are equal to one another, that means more random they are. So is that okay, Professor Sandeep?
Yes, sir. Thank you.
You don't
I
need to,
understood.
yeah, you
I
don't need
I
to call
understand.
me sir, you can just call me Moina, every one of you. So anyways,
Okay.
so this is for this I was trying to motivate. This is the motivation. So more the random a system is, more will be the entropy. So this is the key thing you need to understand. So whenever a system is deterministic, there is no entropy, just like we do it in thermodynamics. This is analogous here. So we come to the first question today. This is I sort of thought I'll start from here itself, but anyways I gave a short introduction to entropy. So I'll give you this example. Say there are 5 red balls in a box, 6 black balls, 2 yellow balls, and 4 blue and 3 green balls. So what we want to calculate, say x is a distribution, x shows the distribution of each one. When you sample from the box, you pick a ball from that box, what is the entropy or the information that you get from that box. So we'll have to see the probability of each of these events occurring. So what is the probability of the red ball being picked? So that's nothing but, it's a very simple probability question. So it's 5 by 20, so it's 0.25. Similarly, a black ball is 6 by 20. So you have 6 balls, and total balls is, you can clearly see 5, 6, 11, 13, 17, 20. So there are 20 balls and the number of black balls is 6, so the probability of getting a black ball is 6 by 20. Similarly, yellow ball is 0.1 because it's 2 by 20, and similarly this blue ball is 4 by 20, and this is equal to 3 by 20. So now we can directly use, these are the probability of each of the events, so we can break this distribution. So we can break each of these probability terms into n terms. So here there are 1, 2, 3, 4, 5 realizations of this random variable. So that random variable can, this discrete random variable can take 5 values. So the entropy will be calculated considering all these 5 values, as I had said. So you take each of this random variable as you take the each realization of the random variable, multiply with the log, and sum them up. So see how close they are to one another. So I'll show this entropy here. So you can see it's 0.25 into log 0.25 plus, so you get 0.3 log base 2.3, and you get 0.1 log base 2.1, and you get 0.2 log base 2.2 and 0.15 log base 2 0.15. So I hope, if my calculations are correct, it turns out to be, I'll just see once again because may have, so if my calculations that I've done previously is correct, it should be 1.54. Hello?
Manik,
Yeah.
Manik, this is Vidya Manik. Will you please explain once more, please?
Yeah, sure. So you can so you want to want the explanation of entropy once more, or the question solution to this question once more?
Solution to requesting.
So you can see that what are the realizations of the random variable x denotes which ball is picked. What values can x take? It can take red, it can take black, it can take yellow, blue, and green, right?
Yes.
Yeah. So entropy is seeing how close are these, or how close or how far, how random is the system. So are there more red balls or not? So for that we take the summation of each log pi into p into log pi. Okay, so for each value of the random variable we will taking pi into log pi, right?
Okay.
So here how many values are there? There are 5, 0.25, 0.3, 0.1, 0.2, and 0.15, right?
Yes.
So that's what I have done. So I have expanded this summation into so this is I think 1.89. You can check the calculations anyways. So it's a log sort of a thing. So you take the log and see the calculation. So in this case you can see that we take each of the probabilities and multiply them with the log value of that. Is that okay? And take the sum of that. That's what I've written. The formula I've just expanded this here. Is that okay with you? Do you have any questions?
Yes, sir. Fine, sir.
Yeah, if anyone have more questions, you can ask, or we'll proceed. So there's one more thing that I wanted you to realize. So initially I was planning to do this after this question. So I had already told you if the system is more random, the entropy would be very high. So I've given you this idea of this question. So when is the entropy maximum? So P1 equal, I will show you where what does this happen if all these Pi's are equal. So there are n realizations of a random variable. So what happens is, what will happen if they are all equal? So example, P1 equal to P2 equal to P3 dot 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 Pn. So what is the value of each Pi? Anyone?
1 by n, sir.
Yeah, that's correct. So because we sum over all I equal to 1 to n, and that's equal to 1. And since they're all equal, so np is equal to 1. So for all I. So this is equal to Pi is equal to 1 over n. Right? Anywhere, anytime you have a doubt, you just stop me there itself. So now, this is what you get. So now if you do this for the entire distribution, so entropy will be, entropy here would be summation of 1 by n log 1 by n base 2 from I from over all n. So there are n terms and all of them are equal, right? So it's n into 1 by n log base 2 1 by n. So this is log base 2n. So we can show that this is the maximum entropy of a system. Of a discrete system, okay, that has n realization. So did you quite understand that why this is happening? So all of them is 1 by n, so you sum over all of them. So in the last case it was log 5, it was 5 cases, so 5 by log 2. So in that case 2.32 was the maximum entropy that system could have had. So we had a lesser entropy than that because there is more lesser randomness than complete disorder. It's not 1 by 4 for everyone, right? Is entropy clear with everyone? I can give you one question, you can try it out. So that will give you a better understanding why this is equal, why equal actually increases the entropy. So let's take a binary Bernoulli random variable, Bernoulli P. So you try to find the entropy of X here. So that is equal to, I'll just write the first line, probability of X is equal to 0 into log probability of X is equal to 0 minus probability of X equal to 1. Bernoulli means you can either take 0 or 1. It's a coin toss. This means a coin toss. So any time you have a doubt, you can stop me. I'm doing just a basic of probability. This is elementary probability that I'm trying to do. So you will just replace, let this be equal to 1 minus p. So this is the definition and this is p. So 1 minus p log 1 minus p, or rather I'll put a plus here and I'll put a minus outside, p log p. I'll just give you, this is a homework and an exercise to do, class 11 maths. Maximize this function. So if you maximize this function, you will see p will be equal to half. So just take the derivative dE dP and put it to 0 and you will see you get a half. So entropy's graph for a 2 Bernoulli random variable is sort of like this. Here it is 1. So I told you maximum entropy is log 2, so it's 1 here. So you can see, you can plot this in any plotter, or you can do it in your hand as well. This is class 11 maths, so I'm not going to waste time on this. If you have a doubt, you can ask me. So this will motivate why does entropy increase when randomness increases. So mathematically, I explain intuitively. You can see it with mathematical equations here. So that will help you. So now let us go to decision trees. So let's solve a decision tree problem with information gain concept here. Let's see what are decision trees and how to build one of them. So decision trees are, that's for this reason I introduced the concept of entropy. So I'll go there first and then we'll come back to this. So decision trees are like this.
Sorry to interrupt, Manik, but it is for this entropy is used for linear regression and decision tree as well, no?
In linear regression is sort of not that important, but decision tree it's important.
Okay.
Because it sort of gives you the idea. I'll come to that why it's important. So what are decision trees? So decision trees has it has a root and you have other branches, other nodes and you have finally leaves. So I'll mark the leaves differently. So just okay, I'll come to that later. So this is the leaves. So these leaves will give you the decision. This need not be a binary tree. It can be any tree, sort of a flow chart. You can think of this as a flow chart. Flow chart to take decisions. And we will not be using any heuristics. We'll try to learn the tree from the data that we have. So I'll give you an example with the decision tree. So let's think of, I'll give you an example. So if this is, I'll give you an example from cricket. So think of this thing. So if it is a cloudy weather, and the pitch is green, pitch is dry. So in this case, so if it is cloudy weather, yes, and this is no. So this is a binary random variable. So if it is yes, and you see pitch is green, then you say yes, then you elect to bowl, sorry. That will help the bowler, so you elect to bowl. Otherwise, pitch is not green, do either, sort of, you can say. So it's cloudy and not pitch is not green. So in that case, you can do either. And when in case of pitch is dry and the weather is not cloudy, that is no and no, so you can bat. Here also you can do either. Here it will be either, a sort of, I guess you understand what I'm trying to say. So you take a variable and see the realization of that variable and try to traverse the tree in such a way such that at the end you get a decision with respect to a task. This is a decision tree, right? If you have a question, you can ask me. Otherwise, we can go to an example to understand how these decision trees are built. So it's sort of a flow chart that gives you a series of questions, and finally when you traverse the entire tree, you get the decision at the end in the leaf node. So I have taken an example here. I've made an example here. So this is buying a car from its features. Okay. I have a few features here. So I have one feature as color, one as mileage, and one as number of seats. So what can we do? So we can take each of this feature and try to see if we can divide the binary tree into, if we can build a tree out of it. So here you can see the color category has 3 possible values, that is white, blue and red. So we will have 3 branches if we divide on color. Then we have mileage that has medium, high and low, and here number of seats is binary. It has 5 and 7. So I'll walk you through these examples that will help you. So I'll give you, so how do you build the tree? So we'll have to try out all possible, say, first combinations. Take each of these features and try to find out if we can stop after a particular point of time and we have a reasonable tree. So how we will know that we'll have a reasonable tree? That's how we'll come to now. So think of, we are using color to create the tree. So let's take color. So yeah, so here I have taken color. So color has 3 possible values. Say it has white, it has blue, and it has red. So just concentrate on in the case of white. In the case of white, how many times do these people buy the car? They buy it 2 times and 1 time. So this is the decision. This is the final output that we need to guess. This is the output that we need to predict. So 2 times out of 3, in case of the color being white, the the user will buy, or this customer will buy the car. So I've written y is equal to 2 and n is equal to 1. Similarly, when the color is blue, one time it will select. I think last day also I shared. You'll get all these will be shared to you. You will get the PDF version also, and everything is shared. So last day's class notes are also shared. This is also shared. So there's nothing to worry about. But you can follow along now only as much as you can. The rest you can take a note when I share. It will already be shared once the lecture is over. So this white, black and red. So you can clearly see when in case of a black color, or rather whatever is blue or black, whatever you think. So you see the next three, you get 2 times no and 1 time yes. That's what I've written here. And similarly, in case of red, you get 2 times white, 2 times you buy the car and 2 times you don't buy the car. So now, how do we know that how much information is there in this random variable or this color feature? So we can see by the initial amount of, so I gave you this example of entropy, right? So entropy is degree of randomness. So one thing we can do is we can have something like initial randomness minus final randomness, and we name this as information gain. If you have a doubt, you can stop me. So this is the intuition that I'm trying to build. So you have some randomness initially and you have some randomness finally. So in a case where this is very, very high, what does this mean? High means the final randomness is very low, which effectively means the feature is good, right? So information gain being high means feature is good. So initial randomness we can measure by the entropy, initial, and final entropy of final. So here you can see, if you just, that's why I tried to show why randomness, entropy is a measure of randomness. So you can see whenever entropy the difference of the entropy is very high, it means that your randomness has decreased in some way, and in that case the feature can be selected. So in this case, in this case of color, so what we see is, so initial random, what is the initial randomness of this system? So it's 5 and 5, so its probability is half and half of buying, right? So the randomness is 1. As I had already told you, log 2, 2. This is maximum since they're equal. That's 1. I showed you just now. So, and what is the final randomness? So that is the weighted average of all this randomness, final entropy. Final randomness will be, so I'm being a loose with my terminologies just for you to understand in layman's term. Final randomness would be a weighted sum of all these random variables, of all these say nodes. Just make it full screen. Yeah. So in this case, you have three particular divisions. You split it into 3 nodes in case you select color as the feature. So you can clearly see the first, so this will have a particular entropy, this will have a particular entropy, and this will have a particular entropy. So what is the entropy of S01? So S01 will have an entropy of S01 is half, or 1 by 3 log 1 by 3 plus 2 by 3 log 2 by 3, right? If you have any questions, you can ask me. Otherwise, similarly, this is also equal to the entropy of 0.2 and entropy of 0.3 is again half 2 and 2, so it's half, so that's equal to 1. So I have sort of calculated this here, so you can see you can check the calculation if required, but I have calculated it for our help, so I don't want to spend time in calculations during the class. It's a very small class. Let's see. Yeah, that's correct. So there are three possible divisions of entropy here. So for S0, S1 and S2. So they have three nodes. You break it up into and you take this weighted sum of this. So how many of the variables were in this first node? There were 3 of them out of 10. Here there were 3 of them. Here there were 4 of them. So that's what we are doing. We're taking a weighted sum of the final entropy. So this is the weighted sum. So I'll just show you the example here. So 0.3 for the first two cases is entropy of 1 by 3 and entropy of 1 by 3. So that is equal to 0.91, 0.91. So you have any doubt, you ask me. I'm just skipping a step here. So I have written this here. In case you have a doubt, you just ask, because this is very important. So both of this are 0.91. So in this case, 0.3 into 0.91 into 2 plus 0.4, 1 minus. So this is equal to 0.0445. So this is the information gain. So you can clearly see there is not much information gain here. Not much information in color. So I'll come to mileage now. So in mileage, you can see if there are three possible different mileages. There is high, medium and low. So I have sort of done the split here. You can see it when you get these notes. So think of your split is this tree is given to you. So when you have a high mileage, all of these cars are bought. When you have a low medium mileage, 3 out of these cars are not bought. And we have a low mileage, 2 out of 3 of cars are not bought. So again, I'll ask someone of you if you can volunteer and tell me what would be this entropy function. So what would be this summation of weight S0i's by S0 entropy of S0i's from I equal to 1 to 3. If anybody can volunteer and tell me, otherwise I'll do it now. So I would understand. If you don't understand, you can ask me. I'll just, in this case, I'll just tell you once again, since nobody is responding. So in this case, in the first case, S01. So what do you see? 3 out of 10 are in this case, and you have an entropy of the binomial distribution of 0 by 3 and 1. That is 0, 1. So this, and then you have 4 by 10 and you have an entropy of, I'm taking this one now, 1 by 4 and 3 by 4. And you have 3 by 10 entropy of 1 by 3, 2 by 3. So this is for S01, this is for S02 and this is for S03. So you don't need to know anything about this. This entropy is 0. I have already told you, because there is no randomness here. You can clearly see one of these random variables is 1. So I gave you this trivial case in the beginning itself. There's no randomness. I put it to 0. And the second thing is 1.
Sir, excuse me, sir.
Yeah.
There would be 3 by 10 in place of 5 by 10. The mileage.
3 by 10 in place of, I didn't write 5 by 10, that's 3 by 10 only. So 3 by 10, sorry for my bad handwriting. Any more doubt? Is it okay?
Sir, okay, sir.
Yeah. Don't call me sir, just call me Moina. That's okay. And then here sorry, bear with my poor handwriting. I have a poor handwriting, so bear with it. So in this case, so it's 4 by entropy of 1 by 4 and 3 by 4. So I have already calculated this 1 by 4 and 3 by 4 and kept it here just to avoid calculations. It's 0.81. So it's 0.4 into 0.81 and 0.3 into 1 by 3 and 2 by 3 also I've calculated. So just now we did 0.91. 0.91. So that's what you'll see to be 1 minus 0.4 into 0.81 minus 0.3 into 0.91. So that is equal to 0.4. So you can see, so the mileage has some information gain. So the final entropy has reduced by a considerable amount. So we'll see what happens with when we break it with respect to seats. Seats also, there is only two possible realizations. We have a 5-seater car and a 7-seater car here. So you can check, I have split it already here. So I split it with, if it is 5-seater car, there are 4 times out of 5 people don't buy it, and if it's a 7-seater car, they 4 times they buy it. So in this both these cases, it's 5 by 10 into. So I for my calculation, for ease of my calculation, I took this, I made up this example so you can clearly see. So 5 by 10 into 2, because both of these entropies are same, right? Entropy of S01 is equal to entropy of S02. So both of these entropies are same. So that's why you just don't need to calculate much into entropy of this distribution of 1 by 5. So 1 by 5 and 4 by 5. So this turns out to be 1. So 1 minus entropy of 1 by 5, 4 by 5, and that is equal to, that is what I've kept here, 0.72. This turns out to be 0.28. So maximum information is in mileage. So you can select mileage at this point and break this, split this decision tree, and you can recursively continue this process by seeing which of the following has maximum entropy. So when you break it into mileage, you'll see that this requires no more split. No split required. No further split. Because there is no entropy here, and out of these two, wherever you will see the maximum entropy, you can decide to continue with splitting or stop with splitting. Is that clear? So continue this process until the threshold. That is that the computer, you write a code such that the entropy of, such that when you stop when the entropy is less than or to be exact, less than some threshold epsilon. So for all nodes, if it is less than some epsilon, you can stop. Else you continue with the maximum, the node that has a maximum entropy, because that has the maximum randomness. You try to break that. Is entropy and the concept of decision tree is clear? So they can go to linear regression.
Sir, one question.
Yeah.
What do you mean by the entropy of a data set which is on the target variable we have to calculate?
That's what I've told. Like when you're breaking this, so what is the output that I'm trying to predict here? That I'm trying to predict the yes or no, right? You buy or don't buy, right?
Yes.
So when I've written y and no, so that what is the random variable here? So this is the random variable. So of our consideration, that is y. So say buy or don't buy, buy. So we're trying to actually compute our entropy on buy. That's a very good question actually. I didn't explicitly say. So entropy of buy, and I'm trying to see how each feature tries to change the entropy of this variable buy, right? Does that answer your question?
Yes, sir.
Yeah. So the target, what are you trying to maximize? We're trying to maximize or minimize the errors. Yeah, correct. So whenever you're trying to minimize the errors, in those cases, the only option is to try and maximize or try and minimize the entropy. Whenever you're trying to minimize the entropy, that means there is no more randomness. You'll not make any error. Yeah. Does that answer your question?
Yes.
Moina?
Yeah.
Now this is a simple classification problem, no?
Yeah.
Yes or no type. What about the regression on which
regression problems generally are tough to deal with decision trees, but we can do one thing: we can break them into small regions. Okay, does that, like, we can break into, I took this, I thought of taking a regression problem, but I did not. Say you have a age prediction problem, so age between 0 and 50. So you can break them into two intervals of 2 and try to predict that, or you can do something. So each of these you can take some variable and try to learn some form of the variable, or try to learn a weight in that form. But generally what we do in regression is we try to come up with this intervals and try to find out the interval of this. So decision trees, since they are discrete number of steps, we can't do very well in the case of continuous system. So with more or less the most applications, what they'll try to do is they'll try to break it into small intervals. They'll try to bin the examples and then they will do it. Make smaller bins, that will help you. Or you can take, people would do is they take some inequalities like this. I just put a bracket here. Is that okay?
Means again we are from continuous variable we are forming the discrete states.
Yeah,
Again.
that because here to do something like regression, linear regression, you will have to again bring in concepts of weight, but the number of states in this sort of a decision tree is finite. But in a regression problem, we can have an infinite number of outcomes. So that is that's not possible directly. So you will have to you have to discretize it in some way. Is that okay? That's generally what is done. So, or you take some intervals and you take decisions according to that. Another thing, if you have a variable that is in real numbers, right? If you have a variable that is in real numbers, take a note of this. If a variable is real, you take decisions. So I'll not write it here. So I'll write it at the end. Variable is real, or a feature to be exact. So you can again take numerical decisions. So as in how? So you can take some inequalities, using inequalities. Say a feature I is between A and B. So, and then you break it into two parts, yes or no. Is that okay? So in case if feature is real, so in that case you can do this. That's the only way you can solve this a feature problem in this case. Is that okay? And you can further break it down as you go along. Is that okay, Professor Sandeep?
I got it.
Yeah. So this is the reason we come to linear regression stuff, to solve problems on real line, in case real number line. So we try to devise a system where we can predict. So we want to form a function that predicts from r to the power n to some r to the power m. So in this case, we'll just maybe say r is equal to 1, m is equal to 1. So if that is a sort of, we try to predict a real number. So this is a multivariate linear regression. That's in a general case regression problem. So what do we do in this case? So we try to find out an approximation. So given y, we try to find out f of x is some approximation, say y hat. So this is a supervised learning algorithm. You are given x comma y given. So we want to learn y hat such that it is almost equal to y. So is the motivation clear for regression? So we want to learn y hat so that it is very close to y. So in the course, ma'am has given examples in which she has tried to minimize the square error. So I'll not do that. I'll give you a geometric view of linear regression. So that will, I think, give you a more intuitive understanding of linear regressions. So what is our objective? We want to learn a y. So before that, let's see this. So how do we project one vector onto another? So I've given you an example here. So if this vector is v, we take a dot product of v with respect to a, unit vector along a, to get the projection along a, right? So this is what the concept will be using. So in order to get v along a, we need to take the dot product. Or we can tell that this is the error vector. The error vector and this vector, this SA vector, are perpendicular clearly from the image. So here we clearly take the dot product of between this vector and the error vector. So you can take the dot product, that turns out to be 0. And if we equate the values, so S is a scalar, you get this to be the value of S. So in that case, you can get a projection variable just by replacing. So I'll show you this in this case. So I'll just, S is equal to A transpose V by A transpose A. This is simple, that simple physics equations that we learned in class 11 was this. This is the same thing. This is sort of the cosine similarity. So this is nothing but equal to along the unit vector of A, you are taking the dot product. So just giving you the intuition here. So if we take a concept of projection variable, we want a projection of this vector V onto this vector A, what will we do? We will do something like this. So we want PV to be sum S into A. So that is nothing but equal to S value we already have in terms of other variables. So A transpose V by A transpose A into A. So we all know by the commutativity of dot products that V transpose A and A transpose V are the same. So we can convert this into sort of V transpose A, or rather not do this. So this is the vector that we have. So in this case, we want V to be outside. So in this case, what can we do? We can take A from this region and try to put the value of V outside. Since this is a vector and this is a scalar, this is a scalar value, so we can put this outside A as well. So this entire box is a scalar. So you can do is A transpose V by A transpose A. Then A transpose by A transpose A, V is your projection variable. So this, if you calculate this matrix and multiply by V, you get the projection along this. Yeah, I'll share everything. There's not a problem. There's not, everything is shared. The NPTEL team shares everything. You'll get the things after the lecture today. So just a second, I'll just share the YouTube link as well. So in case the class meeting stops, you can still continue on YouTube, because we'll take another 10 or 15 minutes after 8 p.m. to complete today's class. So this is the projection variable. So I have written this here. So I wanted to remind you of projection. This will be very useful later on in the course as well, because we'll have to do a lot of projections when we go to PCS and all. So I just reminded you how to take projections of one vector into another. If you have any questions, you can ask me. I just took the dot product and manipulated a scalar outside to get this projection variable. And let us use this similar concept in case of a linear regression. What happens in a linear regression? I'll just show the thing here. The data, how the linear regression data is. So the data is in this form. You have a tall matrix. What do you mean by tall matrix? X1 is this, X2 is this, and sort dot Xm is this. So you have D features and you have M examples. Everything in fair is written in the question, so you can refer to that when it's done. And what we will try to do is to try to predict a y, y1, y2, .. yn. This is our work that we want to do. And how do we want to do it? We want to do it in form of a linear regression. So what is a linear regression? We want to learn a function f of xi such that that is equal to yi hat. So that yi hat is almost equal to yi for all I. So what is this measure of almost equal to? Let me come to that. So we take so this can be, if it's a linear function, so we can take a w transpose xi plus b to be the function. So this is a linear function. So you take w1 x1 plus w2 x2. You take some weight of each random variable and add them to get y hat. So you take a weighted sum of all the features. So what does this mean in matrix terms? So each of this feature, when you take the sum of these features, is going to form a space like this, because d is very less than m. So your y vector, so whatever column space will be doing is, your column space will not be full rank, sort of, or it will not have a solution, to be exact. So what we want to learn here, let me just show you that first. So we want to learn y hat to be x times w. So what is x times w? So x feature 1, x feature 2, dot 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 dot, x feature d. I want to take the sum with respect to w1, w2 and wd. So this is a vector sum view of a matrix multiplication. So it's a weighted vector sum. So it will be w1 xf1, you can, and w2 xf2 dot 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 wd xfd. So you need to understand vectors, how these vector matrix products can be visualized. So this is actually a linear combination of d m dimensional vectors. So basics of linear algebra will say this will not span the entire space. So it will be a plane in the space. This is a subspace that will span, or known as the column space, that it will span. This is the vector that we want to predict. So what will we do? We will try to take the projection of y vector on this plane. So this will turn out to be your y hat, and that will be some linear combination of x vector, that each xi in this plane into w. So we do the same thing again. We try to minimize this error. So I'll come to that now. We project that onto this space to get the weights. So how do we learn the weights? So we can get the exact form here of the weights. So you can see for every I that is in this space, this error vector is perpendicular to this plane. So y minus xw is always into xi transpose is always equal to 0, because they are always perpendicular. This is class 11 maths. When you have a plane like this and you have a perpendicular vector to that, so any vector in that plane and that perpendicular vector will always be equal to, so the dot product will always be equal to 1, 0, because the cosine between them is 0. So that's why for every x this will turn out to be 0. So I'll just write this in matrix form. So since this is for all xi, so these are xi transpose means a row vector, x1 x2 dot 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 x1d, or rather xd. So this is true for all the examples that we have in this question. So therefore we can take the matrix, we can just take the matrix here and take the transpose of that and do y minus xw. So that turns out to be this equation. So you expand this equation, you get x dot y, and you get x transpose xw, and you take the inverse of this to get this equation. So this is your w. So you can directly learn w from this equation. Since x transpose, I'll just write it again here, y minus xw is equal to 0. So x transpose y minus x transpose x w hat is equal to 0. So w hat is equal to x transpose x inverse x transpose y. In this case, if the inverse exists, you can check that this is a positive semi-definite matrix. Inverse may always not exist, but the determinant is always greater than or equal to 0. So in this case, if inverse exists, so we have a closed form solution. Closed form solution. So you can see the dimensionalities to check if it is correct. So x is of the dimension m cross n here. So m examples and n features. So x transpose x will have the dimension of m transpose n. M transpose n. What is this dimension? X transpose y. This is the dimension of m transpose 1. So x transpose y that you have here, so this is n times m into m times 1. So that's, I'm sorry for that. So this is n into n cross 1, and this is n cross n. So clearly see x transpose is m cross n and x is n cross m cross n. So I have written it here, m cross n is x. So this product is n cross n. So n cross n into n cross 1, so that is w hat is of the order of n cross 1. So that's what we wanted. We wanted n features. So there are n features. So we have the solution for n cross 1 dimensions. So this is a closed form solution of this. So we can also do this by, in case we don't have an inverse or the data sample is very large, taking inverse is very difficult. So in that case, we can do gradient descent. So ma'am has covered gradient descent in details in the lecture, so you can go through that. I have also written it down here. So what does gradient descent mean? I'll just give you the intuition and then we can go to the code. Gradient descent. So you have a square function to minimize, any function to minimize or maximize. So you have such a curve that you exist, and you start from here and you say want to reach to a extrema of this function, that is this. So what can we do? We can take some step size along this direction, and you can clearly see. So what the gradient along, so you have any curve, so the gradient is along the differential of the curve. So this is f of x. So f prime of x at a particular, say x0, gives you the direction in which the function increases by the maximum amount. So this is the direction in which it increases. So we'll have to do something. Since we need this minima, so we'll have to decrease this. So what we have to do is we have to move along the opposite direction of the gradient. So what we will do is we'll update the weights as some alpha, that is alpha greater than 0, times the gradient of the function that we want to minimize into w. So what we want to minimize in a logistic regression, since it's an optimization problem, so this projection can also be seen as minimizing the sum of squares. The error of
Good evening, sir.
Yeah.
कहाँ जा रहे हो सर?
Anything you want to?
अब तो मैं रुकी हूँ.
Someone has unmuted unmute his mic.
If this is clear, you don't have any questions, so we can go to what does this Yeah.
Moinak sir, please describe the gradient descent. Actually, mathematically, we are not getting all the things, but put it here in a descriptive way as well, so that it will help us to understand.
So
Please.
did you understand? Okay, I'll come. I'll get to
We
that.
are not getting anything out of it.
No, in this, okay. So say you have a function f of x that is shown by this graph. Okay, is this okay?
Okay.
So at this point, which is what is the direction? What is the derivatives? Derivative is along this. So this is the tangent gives you the derivative along at this point, right? Okay. So what is, since you get the derivative to be the tangent at this point, so we all know if we travel infinitesimally along this gradient in a particular direction, we can actually trace the curve, right? So I'll give you this example.
Moinak, we were talking about the decision tree and information gain, and all, then how we switch it to the gradient descent and how they are related terms.
No, we spoke about gradient. I think you missed the linear algebra in between that we did for linear regression, right? And then
Yes, yes.
yeah, that's why like in between what I did is we showed that the this decision variables cannot be modeled, cannot model this regression problem very well. So we went to linear regressions, trying to estimate f of x as w transpose x plus b. I think we went through this example of how we project a vector onto the space to get the weights of the vectors in such a way. So I've shown it here. So what we want is since y is out of this space, so we want to place it into the space. So you were asking how the gradient descent and this is related, right? So and the decision trees and linear regressions, they are not totally directly related. They are indirectly, they are sort of linear regressions sort of come up to avoid the default or the problems in decision trees to solve continuous problems, continuous random variables. So we want to predict y from the given features which are real numbers using some weight. So in that case, it's very difficult to build a decision tree using all these real numbers. So that's what was the thing that you missed, I think, in between the number 3 question that we did, linear regression in terms of the weights. So I think we missed that. Is that okay now?
Yes, it is session is so mathematical, and we are lost somewhere in between.
So
We get lost.
I'll give you some intuition here. So there's and I'll give you all the intuition actually. So that was like I was trying to give you a different view altogether to just plot this thing into, because the questions that were there in the assignment would ask you to get the information gain and all. So I tried to do the mathematical part as well. So anyway, so I'll give you the view of this. I'll not go to the maths of this. So at a particular point, so if you draw a tangent, it is almost equal to the curve, right? This almost traces the curve if the step size is small, right? This, so I was trying to give you a mathematical pictorial view of gradient descent. Okay. Yeah. So if this is say W, so you have some weight in this form. So if we take a very small step size along this vector, so we'll trace this curve itself, right? Is that okay?
Yes.
So what will I do? This is the vector along which I want to move. I'll take a small step size along this direction to give W. So this is the vector direction. Yeah.
Sir, is there any way to I get a recorded of this class, because I miss entire session due to like office timing? So is there any way I can
get all the recorded sessions? It's on YouTube. I've shared the link also, and NPTEL will share it with you. There's no problem.
Okay. So, like after course or
now only
like
you'll
in
get to
1 or 2 days.
in 1 or 2 days. I've also shared the YouTube link on the chat. You can also see that.
Okay. Thank you.
You can go through that as well. So if you have,
I'm sorry.
yeah,
Okay.
yeah. So try to
Okay.
move
Yeah. I
along
got it.
this.
Let me.
So what is the?
Mhm.
I'll give you an example. So I'll come to why is this true? Limit delta x tends to 0, f of x plus delta x minus f of x by delta x, that is the gradient or df dx, right? Here you'll get everything. There is nothing to worry about. So the derivative can be modeled. So this is one of the principal laws of calculus. So can be modeled as, yeah, somebody please mute if you don't have a question. Yeah. So this is what I'm doing. There's no, so this delta x into df dx plus f of x is your f of x plus delta. So, and if we take this to be delta x to be small negative value say equal to minus alpha, where alpha is greater than 0, so you get f of x minus alpha df dx. Does that give you a like a baseline understanding of gradient descent? I think this will, like, I've done it from the first law of calculus. Does that give you the idea? So, and also I've shown you the picture. So along this gradient, if you move, you will see, you will actually come back all these points, in all these steps, you will come down to this point until the gradient becomes 0. Is that okay, Professor Sandeep? Now I think you get the intuition behind gradient descent.
Yes. I'm trying to understand this.
The gradient is tangent, so every time you move along the tangent, you eventually you trace the entire curve. This is also known as the Euler way to trace the curve. But anyways, you trace the curve and move to the base line. So I've come through this from the first principle also, and also through the graphical view. So in case of linear regression, so we try to minimize this error between, so x transpose w and y, we try to minimize this error. So we want to model y hat as x transpose w. As some, this is what is linear regression. So it's some xn x1 w1 x2 w2 xn wn plus b. I am putting this b inside this x vector itself by adding a column of ones, and then you start. So the x0 will be 1 into x0. So that is the bias term. So whenever you are minimizing this loss function, you will get this point that will give you w. So you can go through the videos that ma'am has shared, that ma'am has actually given. I've also written down the gradient here in matrix form, and I've used it to update w. So before we go to the programming part, I'll just give you one intuition of, in these cases, think of an outlier. So you can see the notes later. So regression problem is something like this. So you have points like this. I give you only the pictorial representation here. I'll not give you any mathematical formulation, just for your understanding. You can just differentiate and see changes. And you get an outlier like this. So if this error is very large, so what will this do? This will try to rotate this line like this. But we don't want this. Since we don't want this, what can we do? We can add a constraint or a bias. So with the loss function of w, you can add a regularization term in this form. So if you add this regularization terms, so you get normalized, or you get a L2 regularized gradient descent. So in this case, the weights will be minimized to 0, because we don't want the weight to be very small. So I'll be adding the sum of all the weights. If the weights become large, this function will be penalized. So the weights in turn will become very small so that this outlier is not detected at all. So did you get the like the pictorial representation? So this is called a bias. So in this case, if you add a bias, the class of functions is reduced. In case of a linear regression, you don't change the mean very fast. So you don't change the values of the weights very fast, so that you do not account for this outliers. So the graph, this does not change. So this is very important. So you, whenever you're doing a practical problem, you generally add this regularizer to prevent this your classifier from going crazy by shifting for all these points. So it cannot be able, it will not be able to detect the outliers. Yeah, this is L2 regularizer is. So did you understand the original cost function, Pramila? So initial cost function is something, yes. So you just add with it some w's, all the w square. So this is nothing but w1 square, w2 square, w3 square, wn square. So if wi is large, so you penalize L of w, okay? You penalize it very highly. The square of it will be very high, right? So I'm just giving you the intuition here. I'm not showing it mathematically for you to understand in layman terms. So is it okay? Are you getting the intuition? So when you're minimizing this, minimize L nu of w. So what will it be? So you will restrain, bias your model to learn smaller weights, right? Is that okay, Pramila? So in that case, this will not rotate, it will not go crazy, it will stay very close to the small values and will not change with outliers, so that you will keep a bias of this of your model, and it will not, the weights, each of the weights that you will learn will be small. Is that okay? Then we can go to the coding. That will be another 2 minutes, it will be done. So I think you get the idea, intuition between adding the L2 regularization. So there is a one interesting thing that all people who are mathematically oriented can see. Adding regularizer makes x transpose x plus lambda I invertible. I have also written the proof above. You can also look at that. So when you add some regularizer, you will see, so L of w will turn out to be x transpose w for all xi minus yi square for all I between 1 to n plus lambda wi square. So in this case, if you assume bias to be 0 here, bias to be 0, and you can, it is not compulsory to do this, this is out of the scope, but I'm just telling you for your interest. You can see that when you try to invert the matrix that we tried to invert previously, you will have to invert this matrix, and this is always positive definite. You can always invert it. Anyways, it's not required. If you are interested, you can try it out. So I'll try and show you the code how to run. You'll also get the Jupyter Notebook code for this. I'll try and show you how to code this thing, and then we'll stop for the day. So is my screen visible?
The screen is visible.
Yeah. So I'll just keep our notes to the side as well, just for you to understand if there is any mathematically. So we showed that w can be this number. W can be x transpose y, x inverse x transpose y. So you can see, I'll just import the basic libraries here, and we'll do code of the gradient descent also, and also by inverting a matrix. So this is basic importing basic functions. In this case, this matplotlib and numpy will be used. I will not use any inbuilt function, so you'll be able to realize and appreciate the. Yeah, any questions?
No, are you presenting a notebook? I can't see the notebook.
I'm presenting my entire screen. It's on the left side. Can you see?
No, I can see only your.
Okay, I'll share it again.
So we can see maybe.
We can see, sir. I think he is logged in from mobile.
Yes.
Okay, it's an iPad. Okay.
Now you'll be able to see. You can just. Yeah. So I'm trying to give you the mathematical insights and also the practical insights. So I'll go through the code as well here. So you can see the matplotlib. I just imported numpy. Numpy is the matrix operation. Last day I introduced it. I told you to go through this numpy functions. So it gives you all the product and multiplication of matrices inbuilt in it. So here what I have done is I have generated a random data set. So I want to fit a line through this data set. So this is the data set generation. There is nothing to see in that. You can check that how it's generated, but this is not important for our purpose of linear regression. So we want to fit a line, sort of best fit line like this. So what will we do? First of all, as I told you, I'll try to learn it via this formula that I showed you. I proved via using projections. X transpose X inverse, X transpose Y will give you Y hat. So that's what I have done here. So this is X transpose X inverse, okay? X transpose X inverse, and this is, I think I'm typing. If you don't cannot see, you just stop me there also. So Y hat in turn is, you use this X transpose X hat to give you inverse into X transpose Y. So that's what I've done. So you can see, like if you can get the linear algebra view of it, the solution of linear regression is just a single line of code. Don't even need any libraries, nothing. Just 2 lines of code will give you the weights that you need to learn for the. This is the bias, since I added 0 once to the beginning of X. So this is the X variable that you have. So that is this Y that you want to learn with Y, and this is the X. You want to learn a function of X to Y. So I added X to this 1 to X1, so that to learn the bias within the same procedure. There is no, we do not do a separate learning for B. So I just concatenated the ones on the left side. So the first on the right side, so this is the bias and this is the weight. This is the sort of C, and this is the gradient or the intercept, and this is the slope of the line. So this is the, when I plot the curve, you can see it learns properly. Similarly, people who try to learn gradient descent, so this is the loss function that we defined. So we take the derivative with respect to something, and then we define this is the squared error loss that I have done here. So I have taken the squared error loss, and this is the gradient of the squared error loss. I have also this code will help you because I am giving you the vectorized implementation of This will sort of improve your performance when you are parallelize in NumPy. So whenever you do a operation with for loops and while loops and loops in NumPy, they actually slow it down line by line. Here you will actually get the help of parallelization with using this form of gradient instead of taking summation of X transpose X. So here I have shown the derivative to be, you can see on the right hand side, I'm highlighting this. So this is the gradient. So if you just change into matrix equation, so you will get the here, if you just change it into matrix equation, you get X transpose X into Y. Just change this into a matrix equation that you have here. Then instead of the summation, this X transpose will be matrix will come outside, and you will have this. When you change from summation to matrix, the later one comes in front with a transpose, and you take a dot product with the outer one, with this one. So that's what I have done here to get the gradient of the entire thing in one go. So these are the gradient function, this is the loss function, and let us see the gradient descent, how the gradient descent works. So I'm initializing weights to be 0, and then I'm updating the gradient at each point for number of epochs. So now I will change. I'll give you this example. Now see, it has learned after 100 iterations with a learning rate of 0.2, and this is the learning curve, how the loss decreases with your number of epochs. So I'll give you another example, then we'll end the session. See what happens, how does it so just to motivate, how does this change when you have lower learning rates? So you were asking how you're not getting the insights. You get insights through this as well. So whenever you have smaller learning rates, you will not come to the minima as fast as you want. You will take much smaller steps, baby steps, and you will be wondering, you will have to take much more iterations to converge. So I did a learning rate, converted learning rate to a very small value here, and then you will see you haven't converged yet. So I'll just plot this and show you. See, this is sort of biased. It is not able to learn lower number of points on the below the line, more number of points above the line. So if I plot this again, so see, it's not being able to learn. It's around something around 0.1. Here it had reduced very drastically. So, but if I run it for more iterations, say let us run it for 10 or 20,000 iterations with a lower learning rate. So means you get more number of steps to converge. So now see, you have converged. So the number of steps I did was much more this time. So now if I plot this function, I am not, sorry, bear with me, I have not written a function for plotting, so I'm having to copy this. So now you see this is exactly equal to the initial equation that we had learned. And if we plot the loss, you can see the loss has finally gone to 0, whereas this here it was not. So if you take smaller learning rates, you may not converge, and you take very large learning rates, you may oscillate as well. So you need to be, I'll give you that example as well, you can oscillate. So you have to sort of be careful, choose an intermediate learning rate. 20 say is your learning rate, and 200 times you are doing this, and then see, you have diverged to infinity. I think in this case plot, I don't think you'll learn anything here. So you haven't learned, you have diverged to infinity. So the learning rate is very crucial. So you haven't learned anything. So even with 2 learning rate, you are not learning anything. And I'll show the plot of the loss function will give you more insights. See, it is increased. Sort of it diverged because its learning rate was so high that it jumped outside. Instead of taking a small step, it jumped to a far away point. So be careful, take a smaller learning rate, not very small, take an intermediate learning rate and learn for a longer period of time. So that if you have any questions, you can ask, or we can end today's session. Do you have any questions? Then you can ask. Otherwise, you can go through my notes. You can ask me if you have any doubts. And yeah.
Moina, I have one question. Can you tell in brief what is the ridge regression and lasso regression? Just for curiosity, out of curiosity.
Oh, lasso regression, right?
Lasso and ridge.
Yeah. So lasso regression and ridge regression. See, lasso ridge is basically the same thing. Lasso is for your logistic regression case, and ridge is for the same thing for your the linear regression case. Okay. So you take a L1 norm. Okay. In this case, you instead of taking an L2 norm, sum of the squares, you take mod of, so I'm writing it in the chat.
Norm, no?
Yeah. Is it visible?
Yes, I have seen that message.
Yeah. So you take a L1 norm, you take the summation of the mod values of each of the weights. Particularly if you have studied optimization, it is very important. It gives you a very nice structure because it can be used for feature selection as well. Because some of the weights, which is a property that it gets most of the weights to 0 and keeps only a few number of weights. You take the sum instead of the squared sum. So I'll just before updating my slides, I'll just mention the lasso regression at the end, and that you can look into. Means I'll just add this as well. So you take L1 norm, means sum of the mod values of each weights, and use that to actually get the to normalize your log function. So in this case, what will happen is you will not see a very large, most of the weights will be 0, so you'll understand these features are not that important. So it can be used, you can try this out when we have done logistic regression, then we can show you that this lasso problem will help you to remove most of these features. So that will give you an understanding which features are important and so on. Is that okay?
Okay, thank you so much.
Yes.
Thank you so much.
Yeah, I'll tell you, please try to bear with the mathematics, because I think then it will get the better flavor of later courses, because those will be like PCA and all. I'm trying to slowly build the concepts. So anything that you haven't understood, I would urge you to go through, especially the linear regression, linear algebra part of it. If you can revise, it will be very helpful. Thank you.
Could you suggest any one more question?
Yes. Yeah.
If you don't mind, could you suggest a good website or MOOC, anything which is
you
good
can
for
see
data?
Gilbert Strang's linear algebra. You can go through a first 10 or 12. Gilbert Strang's book is there for linear algebra.
Could you post that message in chat box so that I will?
Gilbert Strang, MIT OCW 1806, and there's a book as well.
Gilbert Strang's MOOC certification or what? Or it is a book?
It's a book based on linear algebra, basics of linear algebra. You have a book for Gilbert. You just search Gilbert Strang linear algebra book, you'll get it. Introduction to linear algebra.
Okay.
Yeah,
Great.
I think that will be
Thank
helpful.
you.
Yeah.
Yes.
Anyways, I'll be introducing the concept, not like just I did today. But since our limited time, I'll have to rush a bit. Anyways, if you have no more questions, I'll stop the session for today. Is that okay?
Absolutely.
Yeah. So bye. Meet you next week.
Bye. Take care.
Yeah.